Hello, everyone. My name is Alejandro Garcia,
Oliver Real.
and then we're doing our presentation on xenon ion propulsion.
To start off, let me introduce our propulsion system. Xenon ion propulsion is an advanced propulsion technology that uses electrically charged ions to generate thrust. Um, this offers this propulsion system offers efficiency, a very high efficiency, which means a very high ISP compared to traditional chemical rockets, making it ideal for long duration space travel. Uh, but it does come with very little force. Um, This technology is though widely used in satellite station keeping and interplanetary exploration missions, such as NASA's Dawn and NASA's Deep Space One. Next, let's go into how it works. We have a diagram on the right-hand side. It gives like the whole schematics of the Xenon propulsion system. Um, so first, there's different stages. There's around 6 stages uh, to produce thrust. First is the gas inlet. This process begins with xenon gas being introduced into propulsion systems through the gas inlet. Xenon is chosen because of its high atomic mass and inert properties, making it ideal for generating thrust. After that, we have the discharge chamber. Inside the discharge chamber, xenon gas is ionized to form plasma. Electrons are emitted from the cathode which collide with the xenon atoms, stripping them of electrons and creating positively charged ions. The anode also helps maintain this ionization process. After that, we have the magnetic field. We have permanent magnets around the discharge chamber, which confine the plasma, uh, restricting the movement of electrons. Is this is to have the ionization process more efficient and preventing the electrons from escaping too quickly. After that, we have our ion extraction and acceleration. Once ionized, the positively charged xenon ions are drawn towards the accelerating grids. High voltage between these grids create an electric field, accelerating the ions to high velocities. Um, this will create thrust, but before that, we have to neutralize these ions. As the ion beam exits the thruster, it creates a net positive charge. This uh, make the spacecraft become negatively charged, but to not do that, a neutralizer is emitted to give the ion a neutralizing effect. Then after that, the high speed ejecting of the neutralized particle creates a reaction force, which is our thrust. Next, let's talk about the advantages of our propulsion system. Like I said before, this propulsion system has a very high ISP compared to traditional chemical rockets. This efficiency extends the mission duration as well as reduces the overall weight of the spacecraft. Um, our next advantage is long operational lifespan. This propulsion system can operate continuously for thousands of hours, as we see in the Deep Space One and the later side, making them ideal for long duration missions like interplanetary travel as well as satellite station keeping. Our next advantage is precise thrust control. Since we're working with small thrust values, uh, we can achieve highly accurate adjustments in our trajectory, orbit, and attitude control. Lastly is the environmental friendliness of this propulsion system. Ion propulsion does not rely on combustion, which means no bad emissions or bad combustion gases coming out of the system. And xenon is an inert gas, meaning it's non-toxic. Next slide.
And then as for the xenon ion propulsion systems, there aren't very many disadvantages that we can't justify using mission criteria or mission requirements. For example, uh, we do create a minimal amount of thrust using these engines, usually in the magnitude of millinewtons, and that's obviously not suitable for launch procedures. But when we're out in space where there's almost no air resistance and almost no friction or anything acting opposing to the spacecraft, we don't need very much thrust to actually get to where we're going, as we will just keep on accelerating for an extensive amount of time. And then, but that also brings us to these forces actually do make it very difficult to change direct trajectories on the fly. You have to plan them out well in advance in order to make the trajectory that you need plausible, because we don't make enough force to make quick turns or make quick slows or any type of quick maneuvers. And then we go on to high power requirements. In order for these engines to run, they actually do need external power and quite a decent amount of it. I've seen several run about 7 kilowatts of power, and for this, you would need an external subsystem such as a solar panel or an external power um, generator in order to make the thrust. So it adds weight to your spacecraft and it adds an external system that you would need in order to run these engines. And then although xenon gas is environmentally friendly and clean, it is extremely expensive and hard to come by. There aren't very many plants on Earth or very many factories or locations where uh, it's very plentiful. Only a certain amount of plants create a certain amount, and because of that, it's very limited. I found a research paper from MIT about 20 years ago, and it was estimated around $385 per pound. This may not seem a lot when you factor in all of the expenses for these projects, but when you're carrying a vast amount of fuel as you do in these systems, it can total up pretty quickly. For example, uh, several of these projects, fuel alone costs around $13 million. And then we also have the complexity of each system. Um, the engines, of course, are very complex and have subsystems. And with each subsystem you bring in, you increase the likelihood of failure or having a failure point. And of course, these more complex engines are more expensive to maintain, but we can justify this as these engines have proven to be very reliable. As they're not making an extensive amount of thrust force, they usually don't break because of mechanical failures. So um, we could justify that too because we also need these to be reliable because no one's going to be out there servicing this in space when you're millions of miles away from Earth. There's no way to service them anyways, but they are very complex. I believe a noteworthy story is its first application, and its first application was in Deep Space One, which was a new NASA mission launched in 1998 to test the advanced technologies for future space explorations and to demonstrate the capabilities of this new xenon ion propulsion system. And as it was the first spacecraft to use the xenon ion propulsion system, it demonstrated that it was incredibly effective and incredibly reliable for this type of mission. The ion engine propelled the spacecraft to a top speed of 9,600 miles per hour, or in other words, 2.7 miles per second. And of course, it didn't do this all at once. Using its 180 pounds of onboard xenon fuel, um, it took 16,265 hours to accelerate to that speed. But of course, all of those hours weren't designated to just go to a straight line. Some of those hours were to bend the trajectory to get out of other orbits or to do micro maneuvers to do small turns to get back on trajectory. Um, but those 16,000 hours proved um, that the engine is reliable enough to go the distance and to go for the amount of time to do these deep space missions. Although the mission overall wasn't exactly a 100% success, as NASA wasn't able to retrieve their um, their photographs of the asteroids they wanted to initially capture. Um, they wanted to come a couple hundred feet from the asteroids, but because of a crash on board, with the onboard computers, they were only able to get, I think, within 16 miles of the asteroids they wanted to capture. That was solely a software issue. It had nothing to do with the engine. The engine proved its capability in the long term to be reliable and effective. And then NASA went on to do the Dawn mission and the Dawn spacecraft, which did um, essentially the same thing, but was able to accelerate to a top speed of almost double it. However, that that engine was only half as efficient, but uh, this first Deep Space One mission paved the way to the Dawn mission and future missions for deep space explorations.